2 weeks left in the semester here. 6 more days of class. Today's lecture 33. I think we're going to end up having then 38 lectures by the end. Mostly focused on differential equations. So in lecture A, we're doing more applications of basic differential equations and slope fields, which I think I did talk a little bit about before. Not remember it for sure, but I think I did a little bit. Lecture B, we'll get into some physics, mass on a spring. It's also called a harmonic oscillator, and we get what's called a second order differential equation. And we will also convert that to what's called a system of differential equations and look at solution curves in what are called the phase plane, what is called the phase plane of that system. All right, let's consider once again the logistic model of population growth. Essentially this differential equation right here. Although I think I'm going to do like the book does, and I'm going to call the carrying capacity L. So the differential equation here is going to be dy dt. I think the book uses p as the dependent variable for population. But we will try using y equals some constant k times y times 1 minus y over another constant, capital L is what we will use here today, like the book does. This is called the logistic model of population growth. The idea with the logistic model is that when your population is small, when y starts out low, it should increase exponentially at first. But then, once the population gets high enough, the population should level off and approach what you would call a carrying capacity, a limit L for the environment. If the population starts out too high, above the carrying capacity, then you would think the population would decrease. Now, of course, populations don't increase or decreasing along a smooth curve because people or animals are being born and dying all the time. It's really a discrete process, but we are simplifying things. We got Mathematica to solve this with DSolveValue last time. Let me go ahead and put an L in here instead of an N now. And Mathematica produced this for the answer for this differential equation with this initial value, this arbitrary initial value, y0. The formula for the solution looks like this. Let's see if we can first confirm this by hand. Question?
I was going to say, on homework and tests, will we be expected to confirm the general solution by hand?
You should be able to for the examples that we do by hand. Yeah. So this is an example of one that you should be able to do by hand, though probably if I put it on the test, I'd pick specific numbers for K and L to make it a little bit easier.
All right.
Separate variables, divide both sides by y and 1 minus y over L. So all the terms involving y are on the left side. And quote unquote multiply both sides by dt. To get that. It is probably a good idea to, let's say, factor a, let's see, what does the book do? We can write this expression as L minus y over L. And then we can multiply the top and the bottom on the left side by L. We get L dy over y times L minus y. That's going to make the algebra a little simpler to do that. See what I did there? I subtracted these fractions by getting the common denominator of L. 1 is the same as L over L. Here I have a minus y over L, so the minus y goes up there. Then I multiply this entire thing by L over L, which is the same as multiplying by 1. I get an L up top, and on the bottom, the L down there cancels, giving me this. We would now want to integrate both sides. The right-hand side is easy to integrate. K times t plus some integration constant. Let's call it C1. Okay, because we're going to have other C's. The left side, you technically want to use partial fractions to help you integrate it. So we want to write L over y times L minus y as some constant a over y plus another constant b over L minus y. Solve for a and b. We can now multiply both sides by y times L minus y and convert the equation into this form after cancellation. Plug in your special values of y to make it simple to solve for a and b. When y is 0, for example, the equation becomes 1 equals L times A, so A must be 1 over L. And when y is L, the equation becomes 1 equals L times B, so B must also be 1 over L. Plug those in there. Oh, sorry. I thought that was a 1 there. These are L's. So actually these things are 1s. Is that your question? Yeah. So A and B are 1, and the L on the top goes away because of that. So this thing becomes the integral of 1 over y plus 1 over L minus y. You're going to get logarithms involved. You're going to get the natural log of the absolute value of y minus the natural log of the absolute value of L minus y. Minus sign there because of the minus sign there. We've done that before. Chain rule can be used to check it. Also, integrating this with substitution w equals L minus y would produce a dw equal to negative dy, so that's why the negative sign comes in. We could put an integration constant on the left side, but there's no need to. We already have one on the right. kt plus c1. The goal here now is to solve for y. Y is going to be a function of t. You can use a property of logarithms to combine these into one logarithm, like that. You can then get rid of the logarithm by exponentiating. E to this power gets rid of the logarithm, so you're left with the absolute value of y over L minus y equals e to this power. And maybe we prefer writing that as c2 e to the kt, which is okay to do because of properties of exponents. C2 essentially would be e to the c1. Turns out you can get rid of the absolute value signs. Though if you do, you might want to call it c3 instead of c2 now. And now the goal is to solve algebraically for y. Let's do that up here. I can cross multiply. Multiply both sides by L minus y, really. It cancels on the left side. So you just get a y on the left side. On the right side, you get c3 e to the kt times L minus c3 e to the kt times y. And you multiply this by L minus y. Solve this for y now. Bring the y terms on the left. Leave the term that doesn't involve the y on the right. Like this. And you can now solve for y by dividing both sides by this. Y equals c3 e to the kt L over 1 plus c3 e to the kt. That's one form you can leave your general solution in. It's not the form the book does. The book, if you look on page 631, if you happen to have your book, leaves this in another form. What they do is they divide the top and the bottom of this by c3 e to the kt, essentially. Leaving just an L up top. When you divide this by c3 e to the kt, you get a 1. I'm going to put that 1 right there. When you divide this by c3 e to the kt, you get a c4 e to the negative kt. Well, you might as well call that c4 just a plain c. And write it like that. That's the way the book writes it. Actually, this way is perhaps a little bit more ideal, at least for solving certain initial value problems than this one is. But let's not worry about it. You see again what I did to get from here to here? I divided everything by C3 on the top and the bottom. The C here is really 1 over C3. I also divided everything by e to the kt. Question?
So like on a test or in the homework, are we going to be expected to have all these different C's and have them like, so say like C3 equals a certain quantity?
I traditionally am a little bit relaxed about that. I usually don't make a big deal out of it. As long as you don't make a mistake in being a little sloppy, maybe using the same letter C all the time, even though it represents different forms of the constant. And leaving it either one of these ways is probably okay. And again, this is the way the book leaves it. Actually, with this formula, you miss the solution y equals 0. No choice of C is going to make this equal to 0, but C3 equaling 0 makes this one 0. So there are some pros and cons to each formula, but this is the way the book leaves it. If we add our initial condition, y of 0 equals y sub 0, this represents infinitely many answers. L is fixed, but C is arbitrary. Once I add my initial condition, then I can solve for C in terms of that initial condition. Plug in t equals 0, you're going to get this, because e to the 0 is 1. Solve this for C in terms of y0. If you multiply both sides by 1 plus C and divide both sides by y0, you get this. C is going to be L over y0 minus 1, which, if you get a common denominator of y0, is L minus y0 over y0. It's just some algebra there. You can check it on your own. That actually allows me to write the unique solution of the initial value problem consisting of the differential equation plus this initial condition, one function, the unique solution like this, y equals L over 1 plus, replace this C here with that. L minus y0 over y0 times e to the negative kt. And that works as long as the y0 is not 0. However, kind of funny, we're going to go backwards here now. Multiplying everything by y0 allows you to get an answer that works no matter what y0 is. If you now multiply everything by y0, which is okay because you're doing it to the top and the bottom, you get a formula that works no matter what y0 is. It's almost like magic. Okay? And this formula is the same as Mathematica's. They look a little different. The difference is, if you take Mathematica's and divide everything by e to the kt, then you get this one. See that? Divide by e to the kt on top. The e to the kt goes away, leaving you with L times y0 on top. On the bottom, divide that by e to the kt, you just get a y0, which is this. Divide this by e to the kt, you get an e times e to the negative kt, like that. So they are the same thing. Again, if I gave you one like this in the final exam, I'd put numbers in here for K and L to make it a little easier. But the general approach you should be able to do. What do the graphs of these things look like? Let's go back in here and replace N with L. L is the carrying capacity. There's the graph of a solution when the carrying capacity is 15, which could be in thousands of bunnies, for example. Maybe it's bunnies, and the units are in thousands of bunnies that we're modeling the population of. It could be 15,000 bunnies is the carrying capacity of the population, of the environment, I should say. K is 0.1. Essentially, that's the percent rate of growth when the population is small. In percent per unit time. If it's bunnies, it might be percent per month. Okay, they reproduce fast. Y0 is the initial population. 1 here would represent 1,000 monies. And so we see the population increasing initially like an exponential growth, but then it becomes concave down and approaches a horizontal asymptote. And I can change my initial population, see how the graph changes. I can change my K, see how the graph changes. I can change my L and see how things change. And hopefully you think you're seeing changes that would be what you would predict. And if your population is too high to start off with, then it goes down for the carrying capacity instead of up. In the background, and what we're not seeing here is something called a slope field. What is a slope field? A slope field is going to be a plane with a bunch of little line segments drawn of various slopes. It is a slope field. It's like a field of slopes. Don't take that analogy too far. Where each line segment has a slope determined by the right-hand side of the differential equation. At some value of t and some value of y, at some given point whose coordinates are t comma y, we plug that point into the right-hand side of the differential equation. You don't see any t's on the right-hand side of this differential equation, and therefore, for an equation like this, t is irrelevant for the slope field. The slope field only depends on y. If you plug in values of y between 0 and L, that'll be positive, and so will this. You'll get a positive quantity. K is positive too. You'll get a positive slope when y is between 0 and L. When y is bigger than L, that'll be positive, but this will be negative. If y, for example, 2L, 2L divided by L is 2, 1 minus 2 is negative 1. You get a negative quantity there. The slope mark you would make when y is above L, when you're above this line, would be negative in slope. The exact slope is determined by the y value with this formula here. Let's use Mathematica to help us draw the slope field and see how it's related to solutions of the differential equation. Let me go ahead and give the right-hand side function a name. I'll call it f of y. Though it really depends on k and l as well, so I should probably use a subscript here. F sub k comma l of y. It's going to be the right-hand side. It's going to be this expression. K and L are constants. Y is the variable. So for any fixed values of K and L, I'd make a slope field. But then, if I want to allow myself to change K and L by doing the subscript thing here, that will allow me to change K and L, to change the differential equation, essentially, and change the slope field at the same time. The slope field will adjust, essentially, for different values of K and L, and I'll be able to animate it. Formula here is the same as the one on the board. K times y times 1 minus y over L. How do you make a graph of the slope field? You use a command called VectorPlot. Let me make just one slope field by itself first before I try putting it in and manipulate here. VectorPlot. VectorPlot can be used to plot two things, traditionally. Slope fields and something called a vector field. We'll talk about vector fields on Wednesday probably, but today we're talking about slope fields. The way you make a slope field is you make some curvy braces here, and in front of the comma inside the curvy braces you put a 1, and then after the comma you put the right-hand side function for the differential equation here. This function here, same as this function right there, function of y. Let me pick something specific for k and l. For example, I could pick k to be 0.1 and l to be 15, just like in the animation. You plot this over a range of values for both t and y. For example, t goes, like in this plot here, maybe from 0 to 200. That might be one I want to pick there for t. T 0, 200. What range of values for y? Well, in this plot that we made there, y went from -1 to 20. That was the plot range there. I could pick the same kind of plot range up here. Y comma -1 to 20. If I enter this as is, what I'm going to get is a picture of a bunch of arrows that may be not so nice looking. Let's see what happens. That's not too bad. A bunch of arrows. Glancing at these arrows, they seem to have a pattern that followed the pattern of the solution curves that we were seeing, right? Concave up down there, increasing and then leveling off. Decreasing when you're above the carry capacity. That's the essence of what the slope field is showing you. You're getting the path that solution curves have to travel, essentially. Anytime they touch one of these arrows at a given point, like right there, the curve has to be tangent to the arrow. I'm not going to get into the reasons for that at the moment. But how do we get rid of the arrows? How do we just make them line segments, which is what's traditional with slope fields? I always have to experiment with this a little bit. I believe vector scale will make them look nice, and I think doing something like this makes them look nice. Well, it's not quite what I want. Let me try another 0.03 here. That's better. So we don't see any arrowheads at all. How do I know how to do this? I've just done it before, okay? I just remembered what I did. You can look up examples of these things. You can look up VectorPlot in the documentation center. And you'll get examples, and eventually you'd find how to make the arrows go away, just get line segments. These line segments are the mini line segments that I talked about when I drew this picture over here. The slope of each line segment is found by plugging the coordinates of the point into the right-hand side of the differential equation. That right-hand side depends only on y in this case, no t's. So it only depends on the y coordinate. You can see you get different slopes for different values of y, but along any given horizontal line, like this one here, all these line segments have the same slope no matter what t is. That's because the right-hand side doesn't involve a t. So there's how to get a nice picture. In a static picture, I can put this in and manipulate now. As long as I combine plots with show. So there's my regular plot of my solution curve. If I put a show in front of this, square bracket, then an n square bracket here, and then inside the show, put a comma, and actually let's put the vector plot before the regular plot. I'm going to paste my vector plot code right there, put a comma, and then I'm just going to allow k and l to change in the animation. So change the 0.1 and the 15 to a k and an l. That'll allow an animation. There you go, you see the pattern there pretty nicely. The solution curve is following the slope field. Anytime the solution curve passes through one of these line segments, I think it's probably the beginning of the line segment instead of, say, the midpoint. That line segment will be like a mini tangent line to the curve at that point. Because the slope of the line segment is given by the right-hand side, and because the differential equation essentially says, geometrically speaking at least, the solution curve should have a slope at any given point equal to this right-hand side. That's what that equation says. Geometrically, that's how we interpret it. The solution curve should have a slope at any point on the solution curve equal at that point to the value of the right-hand side at that point, which only depends on the y coordinate, not the t coordinate. But now that I have this in the animation, I can change k and l. And not only does the solution curve change, but the slope field changes. Here's changing k, here's changing l. Different k's and l's correspond to different situations, different differential equations, and different solutions. For any fixed k and l, we have one situation. But But the nice thing about this is you can essentially consider infinitely many problems all at once. Different k's and different l's. If I change y0, the slope field stays the same, it's the solution curve that changes. But no matter what the initial condition is, you can see it's got to follow the slope field. I can add more line segments in here, by the way, to make this even more pronounced. If I go back up here and do a comma, vector points arrow, and if I pick something bigger than 15, I think, you'll see more line segments here. If I pick 50, for example, you see a lot more line segments. It becomes kind of a mess. Maybe 30 is pretty good. Let's try 30. That's pretty good. Let's also color the graph itself. So we can see the solution curve in that slope field more clearly. Again, changing K and L changes the particular situation, the particular differential equation you're thinking about. Changing the initial condition for fixed K and L just changes what the starting population is. There's a couple special solutions in here, by the way. When the initial condition is the same as L, then the solution is horizontal. Constant, it's constant function. Also, when the initial condition is 0, which I don't know if I give myself that option. Go down to 0 here. Just barely bigger than 0 there. Okay, let me give myself that option to go down to 0. If the initial condition is 0, then there's no population at all. There's no bunnies to reproduce there unless you actually put them in the environment. So there stays no bunnies for all time. Those two solutions are constant solutions. They have a special name and they play a special role in differential equations. They're called equilibrium solutions because the populations in this case are at equilibrium. Equilibrium solutions. Not all differential equations have equilibrium solutions, but when they do, they're pretty simple. For one thing, they're constant functions, and they can help us understand what the rest of the solutions are doing. Characterize what's going on near the equilibrium solution. Let's do another application. Let's do a physics application this time. Let's go back to free fall. But with this example, let's add in some air resistance. Free fall with air resistance. Let's say the positive y direction is upward. We'll say y equals 0 is the ground. And we've got an object that either is falling all the time, or we could take a ball and throw it straight upwards and let it go up for a while, then come back down. Either way, it doesn't matter. You can think of it either way. The key equation you need comes from Newton's second law. F equals ma, where a would be the upward acceleration, because positive y is upward, which is the same as the derivative of the velocity. It's also the same as the second derivative of the height. We can write that equation in those forms as well. But the key here now is, what is the force? The force is not just from gravity, there's also a force from air resistance. What is F? F equals F grav plus F air. And we need to think about getting the direction of these things right, getting their signs right. Positive y direction is upward, so the force due to gravity points in the negative direction. force due to gravity is negative m times g, where g is the acceleration due to gravity, about 9.8 meters per second squared, and m is the mass of the object. What about air resistance? Does that have a positive or negative sign? Well, it ends up having a negative sign, but you gotta make sure you get the right quantity in here. The air resistance is, you can hypothesize at least, this might not be true for all objects, but you can hypothesize that the air resistance is proportional to the speed. The faster you go, the more air resistance there is. That should make intuitive sense, right? You feel more, you're on your bike, the faster you go, the more you feel the wind. Is it a direct proportionality? Or is it proportional to the square root of the speed? Those are all subjects that we're not going to get into. You have to do some experiments to see which model's better. I think it does depend on the nature of the object. Is it a rock or is it a feather? What is its profile? Is it is it a person falling with a spread eagle, or are they diving? The nature of the air resistance could be complicated by those factors. But we want to keep things simple and hope that the simple approach works. Some negative constant times the velocity is what we want for the air resistance. Velocity has sign, right? Speed is the absolute value of velocity. When you're moving upward in this coordinate system, that's a positive velocity. When you're moving downward, that's a negative velocity. When v is positive, when you're moving upward, this is going to point, this force points in the downward direction. The negative force in that case. K itself here is positive. When you're going downward, when the velocity is negative, this is actually going to be a positive quantity. Negative k times a negative velocity becomes a positive force, meaning it's a force in the upward direction. It's always against the direction of velocity, essentially. So equating these things, actually I'm going to use v. Equating these things gives us a differential equation in the unknown v. We can divide both sides by m and write it as dv dt equals negative g minus k over m times v. You can separate variables and solve for v as a function of time. Here, it's something you should be able to do. I'd probably say go ahead and plug in g as 9.8. Plug in some mass, 2 kilograms or something. Plug in some value of k. The units for k would be force per unit of velocity. Newtons per meters per second, I guess. To make this come out in newtons. You could plug those numbers in here and separate variables and solve this differential equation. It's not too hard. In fact, it's easier than the logistic model. You don't have to do any partial fractions. Let's have Mathematica solve it for us, though, in the general case. And then we'll try and get the slope field in there, and then we'll take our break. So once again, I'm going to use that DSolveValue here. The left-hand side of the differential equation was dv dt, so I need a v prime of t. What was the right-hand side? I put the screen down. Let's repeat again. There was that. Negative g minus k over m times v. Let me actually not replace g with 9.8. Let me just leave it as a g, because then we'd be able to apply this on the moon too. Although there's not much air on the moon. Mars, okay, Mars. Mars has got a thin atmosphere, but it's an appreciable atmosphere. You can actually measure it, whereas the moon is basically no atmosphere. Negative g minus k over m times v. Remember, Mathematica needs you to emphasize that you're trying to solve for a function of t here. So I don't just type a v there, I type a v of t. Even though by hand, I just write a v. And that's actually important to emphasize that by hand you just write a v because then the slope field will only depend on v, not t. So it's a little funny going back and forth between the way you think about it by hand and in your mind and on Mathematica here. But to Mathematica, you do need to emphasize that v is a function of t here. What's the initial condition? I could call it an arbitrary initial condition, v0. We're solving for v as a function of t, and yes, t is the independent variable. This should be able to be solved. It is. There we go. Maybe we want to expand this to make it look a little simpler. There's our formula for our solution function. Kind of complicated looking, though not as complicated in principle as it is. This is just a constant here. And here we have two constants times e to the negative kt over n in both cases, which could be combined into one term if you like. Now let's go ahead and plot this with the slope field, although I'm going to need to change my f function as well. My right-hand side function now depends on g, k, and m. I'm going to have f sub k, m, g of v, not y, if I want to be consistent here. And it's negative g minus k over m times v. And here I do not put a t in there. The right-hand side of the differential equation, do not put a t down here. That's funny. I do it up there, but not there. Make appropriate changes down here. Make this a k comma m comma g. Make this a v. Probably don't need to go so far out in time, maybe just 10 seconds. Let's try now. But let's let y go, or v go higher. Well, this is a velocity. This is not a height. Velocity can be negative. Maybe we should go like negative 100 to positive 100 here. And down here, plug in your solution function that we use DSolveValue to get this thing here. Copy and paste this into here. And then allow g to change. Let's start it at 9.8. Go as low as 1, which would be very weak gravity, and as high as 20, say, which would be very strong gravity. K is related to the object itself. I'll try 0.1 and see what happens. And v0, we can start with an initial velocity of 0, but allow our initial velocity to be negative if we want. I guess we also need a mass. I'll pick this range of masses starting at 1 and being as low as 0.1 or as high as 10. So what we're seeing here is a graph of the velocity as a function of time. And if you start off with 0 velocity, I don't know why this is graphing in such a strange way, I'll fix it after break. If we start off with 0 velocity, our velocity becomes negative and stays negative. You drop something from rest, it's going to move downward faster and faster. Although it is concave up, so actually, even though it's speeding up, the acceleration in absolute value is decreasing. Because this is concave up. If, on the other hand, I start with a positive velocity, well, then the velocity is positive for a while, but so the object is going up, but it does eventually become negative here, so it comes back down. And it's still concave up. So even as it's speeding up as it moves down, the rate of change of the speed in absolute value is decreasing. It is approaching some sort of terminal velocity, as well. We'll see after break. All right, take our break.